We'll now study the most important property of ZTransform. That is, the convolution in time is equals to multiplication in the Z domain. Let's begin with the convolution equation, and this is the convolution equation where we're convolving sequence of xn with yn. We'll assume that xn and yn are causal sequence, so xk is 0 for k less than 0. So when we assume that, then because xk is 0 for k less than 0, then we are not interested in from k equals to negative infinity anymore. We begin with k equals to 0 to k equals to infinity. Now, when that happens, what we can do now is this. We will now take the Z transform of this convolution equation. So this is the convolution. Sorry, this is the Z transform of the convolution of xn and yn. Again, we are taking the unilateral Z transform, so its n starts from 0. We swap the summation and bring the k out, xk out, because we want to focus on yn and z minus n. This is on the way to make this second expression to become y of z. Let's see what happens. We first let m equals to n minus k, therefore little n is equals to m plus k over here. What we now do is that we change this expression of n minus k to become m, and little n becomes m plus k. So we have this equation now here where it almost looks like the Z transform of sequence ym. So all we need to do is to break this unnecessary minus k out, z minus k out, and bring it out to the other side. So this is exactly the Z transform of xn. What about the other guy? This one, because we have moved the minus k out, this looks like the Z transform of yn. You might be wondering that the index that starts from m equals to minus k. So the assumption is that ym is 0. We're assuming that the sequence given to us is 0 before time index n equals to 0, or in this case m equals to 0. So this shows that convolution in time for two causal sequence become multiplication in the Z domain. Let us have an example. Over here, we have a sequence 1, 2, 0, 0. This is time index n equals to 0. This is n equals to 0, n equals to 1, and so on. We have two sequences. It looks like this. 1 and 2. So this is x of n. And the other sequence is h of n, which is 1, 1, 0.5, and 0 all the way. We're supposed to convolve these two sequences. It looks like this is x of n, this is h of n, and we are finding y of n. So we are using convolution of an input signal called x of n with an impulse response h of n to get y of n. Now we're going to perform Z transform of x of n to get x of z. So simply, because this is a finite sequence, this is trivial. 1 at time index n equals to 0 becomes 1, 2 becomes 2 z minus 1. h of n becomes 1 plus 1, 1 plus 1 z minus 1 plus 0.5 z minus 2, since the rest is nothing. So, alright, remember that we are going to use multiplication of x of z or h of z to get y of z. So the idea is this. I will now write x of z first, which is 1 plus 2z minus 1. I will retain h of z for you to see how multiplication will act on h of z. It will distribute. So we have 1 h of z plus 2z minus 1 h of z. So we can now write h of z, because it's 1 by h of z. 2z minus 1 times h of z is this guy. It is simply taking 2z minus 1 times 1 plus z minus 1 plus 0.5 z minus 2. So if you keep looking at this, the first term looks like it is the original impulse response Z-transform. The second one looks like it is a scaled version, which is scaling by 2 and delayed by 1 sample of the impulse response. So in fact, convolution is nothing but this. Anyway, we now add up these two expressions and we get this. So to verify that this is true, the easiest way is to use MATLAB, sending the xn here, sending the hn here, and we'll see that the expression is correct. Now, I'm going to take some time to study this guy. 1 of hc plus 2z minus 1 h of z. What am I doing? Well, remember that this is xn. It is delta n plus 2 delta n minus 1. So this is the input sequence. By linearity, we break xn into two parts. And since the system is linear, we can study the linear system using this input and this input separately. So the top input, let's go and track it. This guy goes through this system, outcomes here. This is h of n. Since this is an impulse, at time 0, this is the impulse response. What about this guy? This is 2 times the delay impulse. The 2 is the scalar multiplication, so 2 comes out here. The delay impulse, delay hn by 2hn minus 1. So the output is 2hn minus 1. And of course, the final output is the sum of these two input signal is basically the sum of these two signals to get here. So in time, we understand how it's being done. Let's see this whole example in the Z domain. What is the Z transform of Hn? This is the Z transform of Hn multiplied by 1, which is the input, because the input is 1. The input is 2, so we are going to multiply 2 by Hn minus 1. Hn minus 1 will become Z minus 1, and Hn become h of z. So this is 2, which is the constant of the input. The first z minus 1 is the input being delayed by 1 sample, and this is h of z. Now, you realize that this guy, 1 of hz, 2z minus 1 hz, you have seen it here. So, manipulating polynomials and distributing them is exactly what we are doing, studying the input response for each input signal separately. Finally, the output is as what we expected in the previous example here. So this two diagram shows you 3 different ways to see convolution. First way is to deal with it from the Z-transform manner using the property of multiplication. The second way is to see the convolution in time, to do it separately, and performing Z-transform on this separate response and adding them up. Okay, so this is a very nice diagram to understand convolution. Thank you.